Hello, astronomy people. All right, so here we are. We're going to start talking about some astro coordinates, how we can find objects in the sky. Okay, so there are two methods to locate objects in the sky. One we've been using all semester so far. We just haven't officially talked about it yet. Really, it's called the horizon system. Right. So basically, all of our measurements that we've been doing when we make star journal entries, our observation project, those are based on the horizon, right? How high above the horizon and what compass direction of the horizon, right? So we call those, they actually have terms, right? Altitude is obviously how high above the horizon. And the compass direction isn't just compass direction. It's what we call azimuth, where we take the compass and we break it into to degrees, right? 360 of them, because the horizon makes a circle around us. So north is 0, straight towards the North Star is 0 degrees in azimuth. Make a right angle to that, to the right, and you got the east, which is 90 degrees. Another right angle, 180 degrees, that's south. Another right angle, now we're looking west, that's 270 degrees. And if you add another 90, we're back to north. So north can represent either 0 degrees, or you can think of it as 360, because you've made one complete rotation around. So it depends on how your point of view is. Anyways, so that's altitude. We've been doing that for a while, right? What we're going to talk about today and really start to investigate is something called right ascension and declination, right? And there's some similarities between the two, but there's definite differences. Similarity is that they're both used to find objects in the sky, okay? But right ascension and declination, or what we call the equatorial system, is based off of Earth's latitude and longitude. It's kind of like they're projected into the sky. Little bit different, but pretty much the same. Okay, so let's take a look at some of these things. This is that Stellarium website I've been using, so I'm going to go full screen on it. Let's see if my face pops up. Yep. Okay, sorry guys. All right, so we're going to do some Astro here, and we're looking north right now, and clearly this is Detroit, right? If you look careful, you could see this building right here. That's the GM building, I'm pretty sure. And then Greektown, I think, is over here. The casino is that really bright thing. I'm not 100% sure, but I think that's what we're looking at. Anyways, folks, this isn't Detroit, in case you didn't pick up on my ridiculously stupid humor. Okay. Hope you recognize this configuration right here. This is the very popular and very well-known asterism, of course, called the Big Dipper here. And the Big Dipper, Merak and Dubhe point to Polaris. So there's our pole star, Polaris. Okay, directly above north. That's amazing. So anyways, what I want to show you, this is altitude and azimuth. Okay, altitude and azimuth, all right, looks like this, where Polaris falls pretty much directly on the north compass direction there, right? And if I wanted to go straight up and look straight up like that, right? 90 degrees from the horizon, straight up. Well, I hope you notice that Polaris is not directly straight up. Polaris is never exactly straight up above you unless you live on the North Pole, right? And we all know who lives on the North Pole, folks. It ain't you, all right? Anyways, that's the only time you'll see Polaris directly above you, right? Because the reality is, the altitude of Polaris, let's take a look at this again. Altitude of Polaris, let's go over here, right here, 42.43 degrees. 42.43 degrees. So basically 42 and a half. What does that correspond to? Our latitude, right? And that's one of the fun facts about Polaris. The latitude of the observer, whoever's looking at Polaris, wherever they are, is going to be the altitude of Polaris. Okay, so for us, 42.5, we're pretty close to 45. Polaris is almost always exactly half up. Not almost always, it is always. Right? If you never leave Farmington Hills, it'll always be in the exact same spot. Okay, so it's a good star to look at for reference in terms of finding altitude for objects, right? So anyways, that's Polaris. And then if you go up another 45 degrees, directly above you is what we call zenith, right? And at this particular point in time, there is nothing located at zenith, right? That changes because the night sky changes, it rotates, right? Everything moves except for Polaris. Okay, so there you go. Altitude, azimuth, good times, good times. I'm going to turn this off, and I'm going to show you now. Oh, yeah, let me show you now the equatorial system. All right, so this is right ascension and declination. So keeping in mind, folks, that right ascension and declination are like lines of latitude and longitude, right? Latitude lines, that's declination, right? It's how high above, how far away in degrees is an object from the equator. Now, in this case, it's the celestial equator, okay? So Polaris now is directly above our north celestial pole, and it has, right, a declination of pretty much 90 degrees, right? Straight up. All right. Declination is permanent. It doesn't change. Altitude and azimuth constantly change, right? And so there's pros and cons to each of these measurements. Altitude and azimuth, super easy for us to use, right? We can go outside, look compass direction, look this high, and boom, there's the object. Right ascension declination is way harder for us to visualize, right? So most people don't use it unless they're using a computer. Okay. So anyways, if I take my point of view here, I'm just going to switch it over to south. Okay. Hopefully we start to see some objects that we recognize here that we've been using. Just in case, I'll turn some constellations on here. All right. So here's our boy Orion. All right. Out every evening now. And it's fantastic observation. One of the cool things about Orion is that its belt, the very top star here, is right on celestial equator. So that means everything above this line right here in that star, this is the north celestial sky. These are the stars in the north sky. Everything below, the south sky. Okay. So that's kind of interesting. And so with this, you can see that the grid system is going to move with the actual rotation of the Earth, whereas altitude and azimuth doesn't. Right, that actually would have been a good thing to show you, is that if you go forward in time, 1 hour, 2 hours, 3 hours, it's hard to tell because we're going hour by hour, but the grid itself is moving. Let's go back. So let's do this. See how fast I can see how the grid's moving with the stars. Now watch this. I'm going to get rid of equatorial. I'm going to go back to altitude and azimuth. All right, click on the time. Fast forward through time. Notice altitude and azimuth don't move, but the stars do, right? Because altitude and azimuth is based on the horizon, right? Whereas the equatorial system is based on the celestial equator, and the celestial equator is going to move, right? So anyway, folks, right ascension and declination are a little bit more precise way to find objects. And like I said, if you have a computer, a telescope, hooked up to a computer, it's using right ascension and declination to find all its objects because it's much more precise and it doesn't change. Okay. And that's my intro into right ascension and declination, folks. We're going to continue talking about this and working with this. But thank you for your dedication in finishing out this video. If you've gotten this far, I'm proud of you. If you've gotten this far, folks, say something about it and I'll give you a point, but you can't tell anybody else, okay? X credit. X credit if you got this far. You just give me a little note saying, hey, Bowsy, I got that far, okay? Huh? I don't know why I'm doing that with my eye. I got something in my eye. I don't know what's happening. Huh?